Good morning, everyone. Today I'm Vishal. Today I'm here to explain about the thermodynamic and economic analysis of performance evaluation of all the thermal power plants. Here, increasing the energy using inevitable is in developing stages of countries and is necessary to achieve higher quality of living. Various parameters cause energy use growth, including industrialization, urbanization, surging in population. Different aspects of life depend on energy, such as agriculture, industry, transport, etc. Approximately 80% of power generation of the world is provided by fossil fuels, and the remaining part works with the other types of energy sources, such as nuclear energy and renewable energy sources. Typically, thermal power plants are assessed by applying energetic performance, which obtained from first law of thermodynamics. First law of thermodynamics. Another criteria for energy evolution energy system is energetic exergetic performance, which is based on second law of thermodynamics. Exergetic performance is an appropriate method for design, assessment, and optimizing thermal power plants. Causes and reasons of irreversibility in the system can be distinguished by exergetic analysis and get better insight into the efficiency of each part of the system. The mentioned characteristics of the exergy performance analysis make it different from energetic performance analysis. Attributed to this fact, utilizing both energetic and exergetic analysis gives designers a significant insight into the system. This type of analysis enables designers to have more appropriate method to assess and determine steps forward enhancement. It is possible to find losses occur in system by using exergy analysis. Exergy analysis facilitates the obtaining energy conversion at energy stages, efficiency rates of different parts of system and points where there are high losses, and helps us to reduce losses. This method is the most appropriate approach in optimizing cycle by given input data. Energy analysis and the idea of its validity have been also carefully discussed, since it is a powerful method in determining energy quality makes it possible to enhance efficiency of complicated thermodynamic systems. Exergy losses can be divided into two parts: avoidable and inevitable. Distinguishing the type of losses based on the mentioned criterion facilitate understanding the process. Electrical power generation system development reviewed by and the special attention are given to the plant efficiency. Evaluated assisting in power plant and by a component-wise modeling and a detailed breakup of energy and exergy losses data. Investigated a thermal power plant works with coal as fuel and analyzed it based on exergy by dividing the system into three parts. One of the coal-fired power plants, which is owned by Turkey government, is selected. In the investigation, zero-dimensional approach is presented to analyze the system from energy and exergy because the benefit of the utilizing this approach is that it makes the results comparable to each similar power plant. Modeling was performed in a unit procedure in order to obtain continuous flow program diagram information from the plant manager and the results of the observations. Modeling process are like as it is illustrated in figure. These obtained diagrams are processed by drawing the mass flow lines in the ceaseless operating condition of the plants. The ceaseless mass flow diagram for each similar power plant. Throughout this modeling approach consists of major factors such as turbines in different working pressures, LPT, respectively, a boiler, various pumps, and generator, and are considered to develop the thermodynamic models through balance equation solving procedure. Any required thermodynamic associated terms such as energy of or exergy or output flow from the turbine, needed pump work, the required heat of the boiler, energy or exergy flow at each point of the plant cycle, associated energy or exergy efficiency for each equipment in the plant, irreversibility terms for each device individually and also for the whole power plant. The fundamental thermodynamic theory of energy and exergy modeling is discussed in further sections. Some assumptions are made in modeling procedure of the power plant. Design conditions are regarded for evaluating the performance of the whole power plant. A single control volume is defined for each equipment in the analysis process. All the employed equipment are working on the basis of steady state thermodynamic conditions. All the gas components in the plant are governed by ideal gas principles. The variation in kinetic and potential energy and their associated energy terms are neglected in this study. The defined reference conditions are 25 degrees centigrade and 1.013 bar, and it is assumed that there is no temperature difference between the equipment control volumes and their close neighbors. We can see the diagram here. So IP where fuel gas, no gas, coal, air, ash, HPH3, HPH1, HPH2, LPH5, LPH1, LPT, IPT, CG. Energy analysis is on the basis of the first law of Energy analysis is on the basis of the first law of thermodynamics. As it is stated in the first law of thermodynamics, the net output work and the associated thermal efficiency are the major performance benchmark. These terms are also critical in case of economic analysis. By employing the corresponding thermodynamic parameters, enthalpy, pressure, temperature, entropy, mass flow rate, and quality over the written balance equation of each equipment, any input or output value can be obtained of HIN minus H1 minus M1, H1 minus H2, HN minus H0, comma 2, comma N are the stages of steam extraction in the steam turbine. Pump is considered as the only work-consuming equipment in the power plant. The pump power is easily obtained by using the WP is equals to M of H out minus H in by MP. MP denotes pump efficiency. Total useful electric output power of the power plant unit is equal to WT minus summation of WP. Following equation can be tell Q is equals to MSH of HSH out minus HSH in plus MRH of HRH out minus HRH in by pump efficiency QP. So calculating the equation, the efficiency of the boiler equation. Boiler inlet enthalpy is not known. MSH in plus HS out MFW HW out. So S and FW subscription are steam and feed water respectively. It should be highlighted that as the feed water heater's outlet temperature is known as at the first step, a similar procedure, a mass conservation balance should be performed to calculate the outlet per temperature. Nth is equals to W net by M cold into LHV, where the coal lower heating value of the coal is presented by LHV and N coal is defined as coal feed flow rate into the burner of the boiler, and coal is equals to the QV by LHV. Exergy analysis modeling is defined as the basis of second law of thermodynamics. The resulted outcomes from exergy analysis can be utilized to check and also monitor the irreversibility location and propose different methods to lower it to the possible least irreversibility value by improving the system performance. A high limitation level of an energy flow are sourced to achieve the highest theoretical work under specified environmental conditions, which is defined by at least two thermodynamic variables, usually temperature and pressure. In this investigation, exergy analysis is carried out to specify exergy efficiency and also exergy destruction rate of each equipment, and also the energy destruction rate of each equipment. Here the equation x in minus summation of x out plus summation of q of 1 minus t naught by t minus summation of q of 1 minus t by t naught by t or t naught by t of out plus or minus w. Here is the right side of the above equation. Heat exchange related terms are shown in the third and fourth of the above equation. Q is defined as the steady temperature heat transfer. Last term depends on the done or given work. Exchange analysis is we can study in this table boiler, turbine, condenser, pump, and feed water heater. In the equation xdb exdb plus exdt plus exdc plus exdp plus exdh, and x is equals to w net by m col by x col. Summation is equals to ext total by w net. Thank you so much.